Hello kids, today we will be reviewing the fourth unit for physics IGCSE 0625. Let's get down to it. The fourth unit is actually a force and motion. Now we do understand that there are forces or something that makes an object move, right? Let's just say you have a mass, right? Uh, let's just say you have a mass, right? And this is a mass, right? M, and it moved from here to this point right here, right? From A to B. Now at point A it was at rest, so something made this object, this mass, move from point A to point B, and definitely something pushed it from the back or pulled it from the front to make it move from point A to point B, or which it covered a certain distance, and it took some time to evaluate to move over this distance. So definitely we can say something made it move, and that something is what we call as force, right? So what is force? Force is actually the ability to change the state of an object. Force is the uh, ability to change the state of an object, whether it is rest or uniform motion, right? Let's just say if an object was already in motion, we can use a force to stop it down or to make it go faster, and if it were at rest, then we can make it move from that position of rest to a certain position over a length, right? So over here we're going to signify that force is actually a product of mass into acceleration, right? So for a force to do a certain object, we understand that a mass is involved, which is accelerated. Why accelerated? Because we're using the term over here uniform motion, and if we disturb uniform motion, we say that a certain acceleration was involved, and that would definitely be the product of these two would be force, right? So force is actually the product of mass and acceleration, and that acceleration could be positive if we're increasing the speed, and it could be negative if it is stopping, or it's in the reverse direction, right? Let's just say a box or a mass was already moving, and a force was applied to break it down, so it would come to a rest, right? Moving, it was already moving, now it became at rest, right? So that is how we can define force. But to understand force, I actually use the Newton 3 laws, which are really important. It's a classical explanation, so I always define as the first law, right? And the first law, I say absence of force, right? That's how I define Newton's first law, right? And when we talk about Newton's first law, we say the absence of force. That means an object uh, would retain its state of rest or uh, uniform motion uh, until or unless acted upon by a force, right? Now that's the first law. That means an object, if it at rest, should remain at rest if no force is acting upon it, or the sum of all forces is zero. That is when the first law is in effect. Or if it's in motion, for example, the movement of Earth in its circular orbit, right? That is also, I mean, Earth does not change its speed, or its motion is not disturbed, so we can say it is in uniform motion. Hence we can say it is not acted upon by any force in this regard while it's moving in a circular path, or it's not acted upon it. No, although this Earth and its orbit is not an accurate example, but just to help you visualize that what uniform motion is like, it is motion or perpetual motion that would remain undisturbed until unless an external force is acted upon it, right? So we can also take the example of a car which is in neutral, and it's remaining, it's moving at a certain speed. Let's say if it's a car, don't mind the way I'm just going to draw the car. All right, I like sticky mans in my classroom. So let's just say if the car was already moving at 45 meter per second, it will retain that value until unless an external force is applied upon it. So this is what the first law looks like. Now second law defines the application of force, right? This discusses the application of force, what happens when force is applied. So we can say the force applied on an object is the product of its mass and the acceleration due to applied force, right? So that's the second law, and that's the general idea of what force is, right? So we can simply define it as F is equal to M into A, right? So that's the second law. I'm not going to define this much. I'm just going to move forward to the third law, which is critically the most important one and the most universally applicable law, the third law of Newton's third law of motion, which is reaction to a force. Now I'm going to give you a very fun example. Let's just say you get to slap someone. Definitely you're going to get a reaction, right? Now that is what Newton's third law is all about, that when you apply force to something, then you're supposed to get a reaction of that. So we can say to every action of a force, there is an equal and opposite reaction, right? So that should be F is equal to minus R. And why the minus? Because the direction is opposite. So let's just say there's a spring, right? Let's take the example of a spring. You pull it down with a force, then definitely the reaction is going to be the other way around, right? The spring will try to react in the opposite way to your applied force. Another example would be a rocket booster, at which it is actually ejecting gases, which is applied force, right? And as of reaction, the rocket booster goes up. This is the most critical application of the Newton's third law. We cannot imagine space flights or sending probes up into space or space travel without the understanding of Newton's third law of motion, where we eject high speed gases as a result of which we get a reaction for the booster to move up, right? And especially when we're in space, where there's no air or anything to push forward with, right? We cannot use propellers or jet engines. We need to depend upon these rocket boosters, which eject mass, that mass which ejects out causes a reaction of the remaining mass to go faster up, right? So this is a very critical example. You should look into this, how Newton's third law of motion is applied to these rocket boosters, right? So this is a general understanding of what force is, and what force can work with. And let's move on to the next topic, types of forces. Now there are several types of forces. I'm just going to critically define few. The first force is like the mechanical ones, the mechanical versions. So I'm just going to look into what we call as force, right? F is equal to ma. Then we have reaction force, which is F is equal to minus R. They're equal in value. By the way, the units for force, as we know, I've discussed in the unit conversion section. It is in newtons, or you can say kilogram meter per second square. As you can see, meter per second square for acceleration and kilogram for mass. So that's the unit. For reaction, it's going to be the same. Then we have tension, right? Tension in string, that is when you have a mass hanging, let's say, so the tension is actually this way. Then we have weight. Weight is also a force, right? This is equal to weight, and weight is again a force which is due to the mass of an object when a gravitational acceleration is acting upon it. So it is again over here, a is replaced by this gravitational acceleration constant g, small g, and this mass remains the same. So that's weight. Then these are few of these examples. Over here I will signify what is the effect of weight, and then we also have upthrust, right? Which is a very odd example. This is also a reaction. You can say, let me just say, over here I must also put a negative sign. The tension is actually opposite to the weight, and upthrust, Fu, is also opposite to the weight. And here I'm going to discuss few cases. If upthrust is greater than weight, then the object must lift up. If this is equal to weight, then the object is suspended, which is in the case of tension, where we actually have weight equal to tension. As you can see, it's suspended. The mass is neither going to go up nor it's going to move downward. It's just going to hang there. And then if Fu is smaller than weight, then the object should fall, right? That's the case in which you can say, I'm just going to draw some vectors, right? If the weight is small but the upthrust is large, then the object should lift up. This is Fu and this is weight. In the second case, right, let's say this is the mass. If the weight and upthrust are equal vectors, then it is going to say suspended. And in the third case, if the upthrust is small but the weight is large, then the object should fall down, right? So you can just understand by the magnitude of these vectors of these forces that where the object is going to move. Now, as I said, in IGCSE it is very odd. I usually get to discuss vectors and scalars prior to discussing motion and forces, but for your course for IGCSE 0625, scalars and vectors are discussed at the end of the unit. So I'm just going to go and discuss scalars and vectors prior to discussing other topics of this unit. So what are scalars, right? So let's define this scalar, right? Scalar quantity. So we did discuss several quantities: base quantities, derived quantities, right? So scalar quantities can be both base quantities or derived quantities, depending upon the fact that quantities uh, that only require magnitude to be defined, right? Those are scalar quantities. For example, we have mass, we've got time. Time doesn't have a direction. You don't tell them that it's 16 seconds to the north or 14 kilograms to the south, right? You don't tell directions with these scalar quantities. Then we also have speed. We always say that the car is going at 16 kilometers per second or 100 kilometers per hour, but you don't say that it's going north, because if you do so, it would become velocity. And the topic of speed and velocity, I discussed that speed is a scalar quantity and velocity is a vector quantity. Then we discussed distance, which was also scalar. It is length, so length is also a scalar quantity. So there are several quantities like this. Also we can have power. We will later discuss power in first block in general physics, and we will come to understand that power is a scalar quantity. Then we have energy. Energy does not have a direction. You don't say that the battery is going to give you power in a specific direction. It just has terminals, positive and negative, and upon which you can take power out. It doesn't matter whether the wire is going to the south or the north or the west. It just gives you power, right? It just gives you chemical. It converts chemical energy into electrical energy. So energies in general are scalar quantities, right, etc. So these are scalar quantities. They only require magnitude. These can be summed as sum of magnitudes, right? So as long as you take the sum of these magnitudes, we can calculate the sum of these values, right? Let's just say time. Let's just say an object moved from A to B to C and then to D, right? So it took some time while moving there, right? As I said, direction doesn't matter, so I just do it in a linear fashion. So it took 3 seconds here, 5 seconds here, and 4 seconds here. So that's a sum of actually 9 plus 3, 12. So total t is 12 seconds. We can simply sum them up, right? We don't need to worry about much of the directions for this, right? Any of these scalar quantities, mass, speed, time, distance, power, energy, any of these we can just simply sum them up, or subtract the values depending upon what kind of calculation we're working with. Compared to this, we have vector quantities, right? So vectors are quite different, right? So vector quantities. Now what are vector quantities? Quantities that require both direction and magnitude to be defined, right? So that means you have to tell them, you have to explain or express the direction as well. Let's just say if I tell you that a person went 15 kilometers to the north, now that's a vector quantity, compared to just by saying that the person walked 15 kilometers, right? It could be in any direction. So that directionless would be just the distance, but when I say 16 kilometers to the north, then it would be displacement, if you remember. So we have examples. For example, we have velocity. It's a vector quantity. We have displacement, which is the position change, unlike the path which we discuss in this distance, right? Then we have acceleration. As said during a discussion of acceleration, that I actually discuss acceleration for velocities rather than just speeds, because acceleration is also a vector quantity. Then force, which is a combination of one vector quantity and one scalar quantity, but still force requires a direction, so it is actually a vector quantity, right? And then we have moment, which is also directional in nature. and then we have pressure, right? That is also a vector quantity. That means you need to define where you are applying pressure in which direction, right? So for example, now I'm just going to make this origin, right? A person starts from O, goes 5 kilometers to this side, right? Let's call it news, right? Okay. By the way, this is why the word news exists: north, east, west, south, right? News. This is how it's written, as a Z, right? A tilted Z. So it went. The person went 5 kilometers to the east and 6 kilometers towards north. So what is the net displacement? The net displacement is going to be this, right? So again, now these arrowheads are important. So I can simply measure the length of this. I can scale this down. Let's just say 1 kilometer is equal to 1 centimeter on my scale to scale, right? These such diagrams are to be solved using specific scales. So you can simply define a certain scale whichever suits you. So 1 kilometer is equal to 1 centimeter, so we can understand that this is 5 centimeters in length on the piece of paper, and this is going to be 6 centimeters on the piece of paper. Now I can simply measure using a ruler, a small ruler, what is the length of this vector over here. Let's just say it turned out to be 7.2 centimeters. So if it's 7.2 centimeters, then it is equal to 7.2 kilometers. So what is displacement? We can say net displacement, and that is equal to 7.2 kilometers. So that's the actual change in position from here to here. It doesn't matter which path he took. I just explained previously that for displacement we talk about the smallest possible or the shortest path, a straight line path between 2 points. And since this position A was the final position, so we need to draw a vector from this O origin to this point A, and then measure the length of this vector, and then use the scale to define what is the actual displacement cover, which is 7.2 kilometers in this case, right? I hope this is a brief introduction about scalars and vectors. It's a very you can say detailed topic, but in IGCSE we just need to understand few basics. We will be understanding these topics more in depth while we are solving past paper questions, where we have to apply this information and solve the questions. Now moving on to the next topic, which is momentum and impulse. So what is momentum? So momentum is actually the measure of motion, right? What do we mean by the measure of motion? That means this momentum is actually the product of mass into velocity, how fast a specific mass was going. Consider this example. I roll a small ball, right? It's a mass which is going at, let's say, 10 meters per second. I think you'll be able to stop it if it's 0.1 kilogram, right? But what if you have 1,000 kilograms of a mass moving at just 1 meter per second? Which one is going to be harder to stop? I think this is going to be harder to stop, because that's a lot of mass to stop. Consider this as an example: car versus truck, right? Let's say both of them are moving at 10 meter per second, and you're supposed to stop them by pulling them from the back. They're moving forward in neutral. Which one is going to be easier to stop? I think car is going to be easier, and this is going to be difficult. Why? Because more mass is going to be there for the truck and less mass will be there for the car. So it would be easier for you to stop the car. It would be very hard for you to stop the truck by pulling it from the back, even though both of them are moving at the same velocity. So that's the effect of the mass when we talk about the measure of motion. Similarly, we have two masses. Let's say we've got two balls which are moving at 10 meter per second, right, and another one which is moving at 100 meter per second. Now both of them are 1 kilogram spheres, right? And when we discuss this, now again, when we try to stop that, I think this is going to be much more harder to stop, and this is going to be easier. Why? Because more velocity means more measure of the motion, and hence it would be harder for you to stop this mass, right? So this is what we mean by momentum. It is actually the measure of the motion of an object, right? So this is actually collaboration. This can be collaborated between the force. For example, we have let's say a sphere. This is 1 kilogram, right? This is at rest, right? So at rest the velocity is 0 meter per second, right? So currently the momentum is actually mv, that is going to be mass into velocity. It is going to be 1 kilogram into 0 meter per second, so that is going to be 0. Now we can duly put in the units, which are kilogram meter per second, right? So this is the unit for momentum. It's taken from mass and velocity. So as the object is not moving, we can say that the momentum is 0. There is no measure of motion of the object, since it is not moving at all, right? Now never try and put mass as 0, because that's where the law of conservation of mass comes in. Mass can never be 0. It can never be created nor be destroyed. So hence mass can never be 0. You can take a smaller value, but to get 0 momentum you need to have an object which is at rest. Now let's say this is the initial state, right? Initial state, right? Now on the same mass a force was applied, and it started moving with a certain velocity. It gained a velocity of 10 meter per second, right? The mass is the same. It is 1 kilogram, right? So what is the momentum? Now let's call this initial momentum, which was 0, and this is now final momentum, which is going to be m into v again. Let's calculate this. It is going to be 1 into 10, that is going to be 10 kilograms meter per second. Now that's the momentum which the object gained after the application of the force. Now you need to understand there is a change of state. So if we discuss change in momentum, right, here is a change in momentum. We are going to call this as impulse of a force, right? It's the force that changed the momentum of the object. It was 0 before, now it's 10 kilogram meter per second. So this change in momentum, what we call as an impulse, can be referred to as pf minus pi, the change in momentum, delta p, right? Delta p. It should be equal to mass vf minus mass into vi. Now since the mass is constant, so it is not going to be different. We can take mass common over here, so I will call this as delta p. Mass is taken common, so it is going to be vf minus vi. Now if you remember, we discussed in the acceleration, the formula for acceleration is actually vf minus vi, the change in velocities over time. So what if I divide both sides with time, right? So this whole thing, let me just highlight this whole thing becomes acceleration, right? So this could be delta p by t, that the change in momentum over the time at which it took to change the momentum should be equal to mass into acceleration, and we do know mass into acceleration is actually force, right? So this is the impulse force that changed the momentum, impulse force, right? Or we can also refer to this as the impulse itself, right? The change in momentum, which is this over here, not this force, is going to be the product of f into t. And from here we can also calculate its units. That is going to be again, the difference is from here we can calculate the value for this. That is going to be 1 kilogram into this difference, and let's just say if it were 10, it was 1 meter per second. Over here, as you can see, the change in momentum is 10 minus 0, so that is going to be 10 kilogram meter per second, right? So in this case, it is going to be force. It would be 10. The value is going to be the same, but the units will change over here since we're talking about impulse now, right? So it's Newton for force and seconds for time. Now remember, Newton second is equal to kilogram meter per second. They are the same thing, except this is F into T, and this is actually going to be mass into change in velocity, right? So this, both of them are actually the same things, right? So you can evaluate this, and again, if you move T from left hand side to right hand side, so delta V by T is going to be acceleration, so M into A is going to be force, right? So you can actually equate this. So this is a summary of what impulse is like. We will be doing past paper questions over there. You will have much better clarity. Just go through some questions if you want to have a brief idea of what you have taken or what you have understood from this topic. And if you still require some clarity, just let me know. I can respond and post some other videos and answer some questions. Now moving on to the last topic of this unit, that is the conservation of momentum, right? What is conservation of momentum? That is, if you have a system of masses, for example, we talk about snooker balls, right? So you have mass m1 which is moving with v1, right? Let's call it u, right, for the sake of bookish symbols. Let's call this u1. It is moving at velocity u1, right? And it goes and collides with mass 2, which is at rest, right? That means v1 is 0, right? So in this case, what is conservation of momentum going to be like, right? Let's just say if it goes and collides, I'm just going to make this collision animation, m1, m2, and now it's the m1 that is at rest, that stays stopped, and it's the other one that moves forward. So v2 is going to be there, right? So in this case, I need to understand that I need to discuss the momentum before collision. So we can say momentum. What is conservation? Momentum before collision should be equal to momentum after collision, right? Now for the initial momentum, the sum of the momentums for this case should be equal to the sum of momentums for this case, right? So this is, let's say, we can say after, and this is before, right? So in this case, we can say it is going to be P1 plus P2, right? Let's call this initial states, right? Initial, it's before momentum, P1I, P2I should be equal to P1F, which is this final position after the collision, plus P2F, right? So in this case, P1I is going to be M1U1 plus M2V1 is going to be equal to M1U2, that's the after collision, which is U2 over here is equal to 0. I think I wrote that. No, I didn't. Okay, plus M2V2, right? And we do know that this and this term is going to be 0, and this is especially for the case of two objects. One of the object is at rest before collision and after collision, right? So we will have M1U1 plus 0 should be equal to 0 plus M2V2, That means m1 u1 is equal to m2 v2, right? So that is what we call as conservation of momentum. Now there are several applications now in which both one was at rest, the other was at motion. What if they were not at rest, right? What if m1 was traveling at u1 and m2 was traveling at a lesser velocity of v1, right? And after collision they collided again, m1 m2, they had a collision. Since m1 was traveling faster, so it's going to bump in from the back, and then uh, m1 is going to be moving with a smaller velocity, and m2 is going to be moving at a much faster rate, right? So in this case the similar thing is going to be there, so it's going to p1i plus p2i initial states equal to p1f plus p2f, right? And this is going to be m1 u1 plus m2 v1 is equal to m1 u2 plus m2 v2, right? And now over here I cannot zero out anything. This is also another form of law of conservation of momentum. When the both of the objects are moving, one is going faster, one is going slower. Now remember, you cannot use the same value for velocities for both the masses. Why? Because in that case they will never collide, right? So there has to be some difference of velocities. One has to go faster, the other has to go slower, so that they bump into one another, and then there's a transfer of energy from the faster one to a slower one, and this is how that change of motion can be defined, right? Now as I said, you need to go through some past paper questions to have a better idea of what you're gaining from this presentation. I'm going to conclude this over here. If you have any queries, just attempt the past paper questions, and if you have any issues, any queries, just let me know. I'll respond, or I'll give you some hints how to get your calculations right, because this topic is discussed more in terms of paper 4 numericals rather than in terms of theoretical questions, right? So there may be a reasoning question with it, but before that you will definitely get a numerical problem through which you have to give the reasoning. Otherwise it doesn't actually come as an independent reasoning question, right? Thank you for time. Bye bye.